So in this video, we're going to look at solving absolute value equations. When we're solving absolute value equations, we essentially have to treat the absolute value as its piecewise definition. So we're going to end up with a couple of equation cases, basically, depending on the different parts of the domain. So let's look at this first one, the absolute value of x plus 3 minus 2 equals 3x. I am going to move the minus 2 over. I'm going to turn this into the absolute value of x plus 3 equals 3x plus 2. This isn't strictly necessary, but I do find that when I can easily isolate the absolute value, it helps me make fewer mistakes with signs and so on. So what I now want to consider is the critical value for this absolute value, and that's the point that makes where it is 0. What value of x makes this 0? And that's negative 3. The reason I do that is because that's the value that splits this into the parts of the domain. We have our first case, which is if x is less than negative 3. And then we have our second case, which is if x is greater than or equal to negative 3. And in each of these cases, I'll have a different equation, basically. Because if x is less than negative 3, then x plus 3 is less than 0, which means that the absolute value of x plus 3 is the opposite of x plus 3. So in this region of the domain, the equation that we're solving is negative x plus 3 equals 3x plus 2. Or in other words, negative x minus 3 equals 3x plus 2. Negative 5 equals 4x. So negative 5 over 4 equals x. But hold on a second here, because this equation is only valid for values of x that are less than negative 3. If x is greater than negative 3, we have a different equation. So because negative 5 over 4 is not less than negative 3, we reject it. There's actually no solution within this domain. Graphically, we can understand what's happening. We'll explore the graphs of these in class. But if you wanted to graph on your graphing calculator the difference between the absolute value of x plus 3 equals 3x plus 2 and find that point of intersection versus negative x plus 3 and 3x plus 2, I think you'll see what's going on. But we'll look at that in class. For now, just know that if the solution you get is not in the domain, then it doesn't apply. So because our domain here was x is less than negative 3, negative 5/4 must be rejected. If I consider the other case, that's where x is greater than or equal to negative 3. Well, if x is greater than or equal to negative 3, then x plus 3 is greater than or equal to 0. So pick any number greater than negative 3, negative 2, for example. Negative 2 plus 3 is going to be a positive number, which means that the absolute value of x plus 3 simply is x plus 3. So in this domain, the equation we're solving is just x plus 3 equals 3x plus 2, which means that 2x is equal to 1, so 1/2 equals x. Now, considering my domain, this is values of x that are greater than or equal to negative 3. Well, 1/2 is greater than or equal to negative 3, so that is not a problem, so this is a real solution. Negative 5/4 was an extraneous root, but the actual solution to this problem is x equals 1/2. So let's consider what happens if I have two absolute value expressions, because now I actually have two critical values. I have a critical value of 3, and I have a critical value of 4. So if I look at a number line, this actually divides my domain into 3 regions. I have case 1, where x is less than 3. I have case 2, where x is going to be between 3 and 4. I'm going to include the 3, but I'm not going to include the 4. That's a personal choice. It doesn't matter where you include each of these numbers. And case 3 is going to be where x is greater than or equal to 4. So in each of these cases, I have to consider what's happening with both of these absolute value expressions. So if x is less than 3, then x minus 3 is less than 0. And 4 minus x is greater than 0. Pick a number that's less than 3, so 2, for example. 2 minus 3 is negative, but 4 minus 2 is positive. So that means that in this region, the absolute value of x minus 3 is the opposite of x minus 3. But the absolute value of 4 minus x just is 4 minus x. Which means that in this part of the domain, the equation that I'm solving is the opposite of x minus 3 plus 4 minus x equals 7. So solving that really quickly, minus x plus 3 plus 4 minus x equals 7. I get negative 2x equals 0. so x equals 0. And 0 is less than 3, so this is an acceptable solution. It fits in the domain. Going on to the second interval, if x is greater than 3 but less than 4, so let's say, for example, the number 3.5. X minus 3, well, 3.5 minus 3 is going to give me a positive number, so this is greater than or equal to 0, which means the absolute value of x minus 3 just is going to be x minus 3. And 4 minus x, well, 4 minus 3.5 is a positive number, so this is still going to be greater than 0. So the absolute value of 4 minus x is 4 minus x. So in this interval, the equation that we're solving is x minus 3 plus 4 minus x equals 7. Well, the x minus x actually cancels, and I'm left with 1 equals 7, which is not a true statement. And so what that basically means is that there are no solutions in this interval. In fact, between 3 and 4, if I were to look at the graphs of absolute value of x minus 3 plus absolute value of 4 minus x and y equals 7, they would be parallel in this interval. So there are no solutions at all. And then the final interval, when x is greater than or equal to 4, if I pick a number bigger than 4, say 5, then x minus 3 is going to be greater than 0. 5 minus 3 is a positive number. But 4 minus x is going to be less than or equal to 0. 4 minus 5 is a negative number. So the absolute value of x minus 3 just is x minus 3. But the absolute value of 4 minus x is going to be the opposite of 4 minus x. So in this region, the equation that I'm solving is x minus 3 minus 4 minus x equals 7, which is x minus 3 minus 4 plus x equals 7. 2x equals 14, which means x equals 7. Looking at the domain, 7 is greater than or equal to 4, so that is an acceptable answer, which means that overall this equation has two possible solutions, 0 and 7. One from the first interval, one from the third, and none from the middle. And finally, we're going to look at what happens if I have an absolute value where I have a quadratic. So in this case, I do still have two critical values. My critical values are -3 and 3, because if either of these values were substituted for x, I would have 0. So I have 3 intervals, 1, 2, and 3. But what ends up happening with quadratics is often 2 of the intervals are the same. So if I think of 1 and 3, if I take a number that is less than -3 or greater than 3, in either case, I end up with x squared minus 9 being greater than 0. So for example, -4 squared would give me 16, minus 9 is a positive number, but positive 4 squared also gives me 16. So because of that symmetry of quadratics, the outside intervals will be the same. So x squared minus 9 is greater than 0 in both of these intervals, which means that the absolute value of x squared minus 9 equals simply x squared minus 9. So for both case 1 and case 3, the equation we're solving is x squared minus 9 equals 16, which means x squared equals 25, which means x equals positive or -5. Positive 5 is greater than 3, -5 is less than -3, so both of these solutions are acceptable. It's the second case that's different. So in case 2, if I were to pick a number between, so -3 is less than or equal to x is less than or equal to 3, if I picked a number between, for example, 0, 0 squared minus 9 is less than 0. So in this case, the absolute value of x squared minus 9 is the opposite of x squared minus 9. So in this interval, the equation that we're solving is negative x squared minus 9 equals 16, which is negative x squared plus 9 equals 16, which is negative x squared equals 7, or x squared equals -7, which is impossible. So there are no solutions in this interval, and our only two solutions are the solutions from interval 1 and interval 3, which we found in the first step.